Okay, everyone. Looks like I have 1600 on the. Let's get started with this afternoon's Northern Arizona University School of Forestry Seminar Series. This afternoon, I have the amazing pleasure of hosting Dr. Andrew Hudak. Dr. Andrew Hudak got his PhD in 1999 from the University of Colorado. From 1999 to 2001, he began working for the U.S. Forest Service as a postdoctoral researcher with the Pacific Northwest Research. Since 2001, he has worked as a research forester with the Rocky Mountain Research. He currently studies biophysical relationships between field and remotely sensed data, including estimating above ground biomass carbon across the Western Landsat time series and other environmental data, predicting fuel carbon loads from 3D point cloud metrics at multiple scales, and relating fuel consumption to energy flux and fire effects. With that, it's amazing to have you here, Dr. Hudak, and thank you for your support and your coming presentation. With that, take it away.
All right, thank you very much, Alex. I greatly appreciate the invitation to speak to you guys today about a topic that has come to interest me a lot, and that's fuel consumption. So as an overview of what I'll talk to you about today, I'm going to introduce this topic of fuel consumption for source fuel characterization, which is a big constraint on consumption, and then resulting emissions estimates. As it turns out, I'm not an emissions expert, but emissions is a big concern of the fire community, and it's actually driving a lot of this research. Sorry, I got to close my window. There's a truck outside. Apologize for that. So I just finished drafting a chapter with a colleague on the different approaches to estimating fuel consumption, and I'm going to go over that a bit today as a transition into then some methods and results, presenting 3 different approaches today on different ways to estimate fuel consumption. But I'll be focused on the one that's underlined, what I call the indirect approach using measurements, local measurements, largely relying on LiDAR collections, pre and post fire. And that graphic you see on the right is a LiDAR point cloud at the scale of a field plot. Okay, so do fuels matter? Well, of course they matter very much. And we're all familiar with the fire behavior triangle, where fuels, topography, and weather determine fire behavior. But consumption is really at the center of a lot of these processes. It produces emissions, it relates linearly to heat flux, and it has a big effect on fire effects. And I think, as you'll see later, a map of consumption actually is a more physically based estimate of fire severity. So as I mentioned, emissions research is actually driving the funding for a lot of this work. And what we tried to impress in this chapter I worked on with Nancy French, is that fuels are so heterogeneous. They vary at fine scales in space and time, and natural fuel beds are composed of different varying fractions of litter, duff, herbaceous, woody fuel, fine and coarse. There are canopy fuels, there are understory fuels. And so it's a complex series of materials that have very different burning properties, very different fuel moisture dynamics and such. So all of those variables greatly influence how much of the fuel bed burns in consumption. So to summarize how to estimate consumption, I'm introducing these ideas of the indirect versus the direct approach. With the indirect approach, we're using model-based estimates to get at the fuel loads and then modeling how much of that fuel burns in consumption. Or we're using indirect measurements such as from LiDAR pre and post fire point cloud data. Whereas the direct approach, we're actually using active fire measures. So as it's happening, we are inferring consumption from the amount of energy release. So because consumption is a process, that's actually a more direct path to estimating it. But all of these different methods have their own advantages, but also their own challenges for measurement. And that makes quantifying consumption actually quite challenging. So there are several airborne emissions campaigns that are driving the study of consumption. And it sort of began with a NASA project that I'm leading, and we are mapping biomass across the US West where we have available LiDAR coverage. And it turns out that the techniques to map biomass actually are very transferable to mapping fuels, different fuel components such as canopy fuels, but even surface fuels or properties like crown bulk density. So the map at the right here shows existing LiDAR coverages that we are actually processing into metrics for predictive modeling for biomass and fuel attributes. The pale green areas indicate largely planned collections. This map is a couple years old now. Some of those have been collected since. So the coverage of LiDAR continues to expand. It's not as extensive as in the eastern US. And you can see on the eastern boundary of this figure, a lot more pale green coverage. And it kind of looks like that more to the east. The goal here is national LiDAR coverage. And USGS is promoting this because they want a 1 meter digital elevation model for an updated NED data set, national elevation data set. But as you may be aware, LiDAR point cloud data have a lot of other applications too, besides the ground surface. Forestry, principal among them for my interest, and now more recently fuel mapping. So a question here is, well, how can we use this information for informing not just fuel maps, but potentially consumption maps? And we are pursuing an opportunistic strategy where if a wildfire burns through an area that has existing LiDAR, then that's one that we should select for sampling on the ground, airborne sampling, and post-fire measurement, because we already have this advantage of the pre-fire LiDAR data to provide that fine scale information on vegetation and fuels. When we can take advantage of those opportunities, then we only have to invest in post-fire LiDAR collections. That saves us money and allows us to more effectively sample a greater number of burns and use our resources, limited as they are. So the first measurement campaign we got involved with was 2 NSF funded projects. The aircraft was, for these 2 projects, they were both based in Boise. And so every morning they would have a morning briefing and they would look at the weather situation, the plume dynamics, and decide, well, which fires are we going to go sample? So where there's existing lidar coverage was just one of the criteria that they considered. But it was an active fire year. And as we bet, quite a few fires actually burned through areas with existing lidar coverage. And that's the ones that are indicated by the white stars are those that were flown, where the smoke plumes were flown on at least one day, and where we went on the ground and did some on-site fuel measurements. The following year was the FireX AQ campaign, which is a combined NOAA-NASA effort. And 2019 was not as active a fire year, but the West is a big area. There's still plenty of fire out there to sample. And so that year we focused on the Williams Flats fire in Eastern Washington. And then these two fires that you've probably heard of there on the North Kaibab, Castle and Ike's fires. Not only were they measuring airborne emissions, but they had another aircraft, an ER-2, flying high altitude to collect thermal infrared measurements that could be used for estimating fire radiative flux. Other people are actually analyzing those data, so I won't get into that today, but it is a method for estimating consumption that I'll mention again later. So anyway, those fires are indicated by the yellow stars. And then finally, we have some prescribed fires that we're including in the mix here. These are funded largely by Joint Fire Science through the FASME project. And these have been focused on the Fish Lake National Forest in Utah. There are actually, there was actually, in 5 years ago, in 2016, we did a site visit to North Kaibab because they have a very active prescribed fire program there. So the intention was for FASME to actually work with those managers to do a lot of pre, during, and post-fire measurements. But then the funding was reduced. So they've been just doing some fires. We've been doing some fires at Fish Lake only to this point. But there is still interest in working on the North Kaibab. Okay, so what are these different approaches for indirect versus direct estimation of consumption? So I'm going to have a couple equations here, but I think they help to explain the contrast in the methods. So here's the indirect method. It's usually a model-based approach where you estimate the amount of biomass consumed by the area burned, by the pre-fire fuel biomass times a burning efficiency to give you your consumption estimate. The direct method uses fire radiative power measurements that are collected as near to continuously as possible, but usually there's time intervals in between. When you integrate those FRP measurements over time, over the duration of the fire, then you get an energy estimate. When you multiply that by a combustion factor, you convert energy to mass, and that's how you then get a mass estimate for the consumption. So that approach, that direct approach, what I'm calling the direct approach, is based on Martin Wooster's seminal paper from 2005, where he showed in experimental small fires how the combustion rate is linearly related to the FRP that you can measure from the fire. And that's a unit of power, which is a watt is like a joule per second. So then when you integrate that over time, you can get an energy estimate in joules to compare to the amount consumed. And then what I'm going to spend most of my time on today is this other approach to the indirect method, is what I'm calling it, where rather than model the consumption, we're actually measuring it. And this is the simplest equation. We just take the pre-fire fuel load mass minus the post-fire to get an estimate of consumption. And if we can do that with LiDAR data, then we actually get a map of consumption, which I think is really powerful. So now moving on to a little more description of this model-based approach. So kind of the operational way to do this is using Landfire products currently, because they are available nationally, and Landfire maps vegetation characteristics and fire regime characteristics. Fuel is among those. It's largely based on Landsat satellite data, which does not have the same sensitivity to fuel and vegetation structure as LiDAR. But we don't have national LiDAR coverage yet. We do have Landsat coverage, and we have the temporal dynamics and the disturbance that Landsat time series can capture. So this is going to remain an important part of the equation, if only because we capture those temporal dynamics. This was largely developed by Roger Ottmar and others, this what's called the fuel characteristic classification system. So this is a field measurement based database where fuel attributes are summarized by fuel bed classifications. So they're not really location based, they are classification based. And Landfire took those classifications for different fuel and vegetation types and related them to the Landsat imagery to generate maps. So here is what's called an existing vegetation map of the US. So this is one of the many Landfire layers that you could download and use. And you can see how complex it is. There are 211 different EVTs. Well, each EVT actually has a number of FCCS fuel bed types. So the amount of fuel bed complexity represented in the FCCS database is actually more than is represented in this map. But you still, to be practical, you need to summarize it somehow. So that's what Landfire is doing. And indeed, Nancy French, in her work to develop the North American Wildland Fuels database, has added considerable value to the Landfire products. What they've done is they've taken that field database that comprises FCCS, and they've used those measurements in the database to represent the heterogeneity in fuel conditions that are out there for a given fuel bed type. And then they've fit these distributions to that field data, and then they can use those distributions to describe uncertainty in the fuel bed estimates. This way, you're not just assigning a mean estimate for a given fuel bed type, and you capture the uncertainty. And that's really important because fuels are so variable. In the middle column there, you can see all the EVT groups, and then they can be summarized by these different fuel components. The live over here, can you see my cursor?
Yeah, Andy, we can.
Okay, perfect. So you got the live fuel bed components, the trees, understory, shrub, and herbaceous. You've got the coarse woody debris and the fine woody debris fractions, and then litter and duff on the forest floor. So all these different components go into representing these different fuel beds, which then get further lumped together into these EVT groups. And to get a representative sample across all these different fuel components, like are represented in these graphs, they've grouped them by EVT. And so that's how this North American Wildland Fuel database works for getting a measure of variance for a given EVT. And then when you have that measure of variability, you can assign that in turn to the emissions estimates that you predict from a model, typically using the consume model. So then your resulting emissions that you're predicting have a distribution. They're not just based on a mean. So that's a powerful aspect of the model-based approach that makes it highly useful for emissions estimation, which tends to work on a larger scale domain. Now in this other approach that I'm more focused on, because I'm more of a LiDAR expert and I work more at the landscape level, is this indirect measurement approach. And this is where I'll focus on these two fires from the Fire XAQ campaign. So as you know, LiDAR is very sensitive to vegetation and fuel structure. And so if we can relate the LiDAR point cloud data to estimates on the ground, we can fit models to predict those fuel attributes from the LiDAR data and then generate maps. We'll do that pre-fire and post-fire with pre and post-fire LiDAR collections, and then difference the maps to get consumption. So just a couple slides here to talk about LiDAR metrics. So the LiDAR point cloud data are kind of hard to use directly. There's so much information in there, and it's apparent just visually. You can see the tree crowns, you can see the understory and clutter on the ground that correlates to fuels. But it's 3D. Things have come a long way in the last few years with software packages to manipulate this information, but still what works most effectively is to reduce this high volume information into rasters that represent the distributional statistics of the height distribution captured in this point cloud. So statistics like the maximum height, the 95th percentile, mean, etc., those themselves are efficient predictors, efficient descriptors of the height distribution that we can use as predictors in our models. Similarly, we can summarize the point cloud into density metrics. We can summarize just the upper canopy points because we've got the Z measurements. We've got the ability to slice and dice this point cloud into these strata. We can look at the mid-story and we look at the understory. And then most important for fuels is this ground and near ground stratum of returns. So as you'll see, a lot of the metrics selected for models predicting surface fuels especially are going to be these near ground returns, as you would expect. So here we mostly use random forest. Sometimes we use regression models, but we like random forest because it's so flexible. It's non-parametric. And so we can throw a whole bunch of candidate metrics at random forest and let it tell us which of the metrics are most important for predicting a given response. So in this case, the response variables are canopy fuels, summarized from our field measurements, or surface fuels, summarized from our field plots. And I don't want you to understand what all these different metric codes mean, but they're sorted by importance values. So at the top of the list is what random forest is telling us is the best predictor for these canopy attributes here on the left and then surface attributes on the right. And random forest gives us two different measures of variable importance. What it does is it bootstraps the data through many iterations. And by removing a given predictor and refitting the model, it can, over many iterations, many forests, tally up the nodes of that classification and regression tree and look at the effect of removing a variable on the incremental mean squared error, or on the Gini index, which is a measure of node purity. So they tend to give you similar results. And so for example, at the top of the list for canopy fuels, this is the 50th percentile. That would be the median height for the returns of 2 meters or greater in height above ground. And over here on the surface fuel model, this is the 25th percentile on top based on all of the returns from the ground all the way to the top of the canopy. So you can see that across these, there's height and density metrics. And so they are just various distributional statistics. So I'll just jump ahead now to the selected variables, those that are near the top. And here they are represented here. So our models we're using for fitting in this case, this is still preliminary, but we're just using 5 metrics from all those dozens of metrics that we're generating as candidate metrics. So then when we look at our predicted fuels, by those models versus observed on the ground is pretty rough, honestly. This is preliminary, but we're only predicting about 30% of variation. I've seen better, but I've seen worse too. And we don't actually have many plots here. This is based on the Williams Flats fire, and we had 20 plots, which is not very many to describe complex fuel beds. But they are at least significant. And what I like most about these models is there's not much evidence of bias. The red lines of best fit fall close to the 1-to-1 line. And so that's encouraging. Also, when we then apply these models to the gridded LiDAR metrics, those same 5 metrics for those 2 response variables that are gridded across the landscape, then we can generate the canopy and why did that happen? And surface fuel maps. So we can do that from the pre-fire LiDAR and the post-fire LiDAR. And that's what these maps here represent. When we difference the maps, then we get maps of consumption. And so these maps represent canopy fuel consumption and surface fuel consumption. The models themselves, the fits were pretty noisy, but then if you were to use these maps to make your decision, you know, upon aggregation, the noise in the maps, the noise in the model that can translate into noise in the maps tends to average out. So because that best fit line was close to the 1-to-1 line, I'm pretty confident that these estimates are pretty accurate or unbiased, even if they're not very locally precise for a given pixel. Another reason it gives me confidence in these maps is just the pattern of consumption. So if you think about where consumption is higher, where you see the warmer colors, that should correspond to higher severity, right? Because that's where more heat was released and you would expect more fire effects. And indeed, if you just look at the traditional delta NBR map, you see very similar pattern in that map as in our consumption maps. So the delta NBR maps are sort of the standard indicator of severity, but delta NBR is, you know, a unitless index. It tells you the delta NBR, which we consider an indicator of severity, but it doesn't tell us anything else about the environment that's sort of like in physical measurement units, whereas consumption, that's you know, like megagrams consumed per hectare. That's a physical estimate, and that makes it a lot more powerful. So I also overlaid the 20 plots that we put on this fire. So these are distributed across the range of conditions that, and actually the delta NBR map proved useful for stratifying the landscape, for putting in those fuel plots so that we can capture the range of fuel conditions in our sample. So they're in high severity areas, moderate, low, and also unburned. We want to capture the unburned fuels to capture the full gradient of fuel conditions that are out there post-fire, because not everything burns, and you know, things burn to varying degrees, of course. Okay, so now moving on to the North Kaibab. So 2019, we had 2 fires there that we're interested in, the Castle Fire and the Ikes Fire. Those are shown in red here. And I also have outlined here the existing LiDAR collections for the North Kaibab, and then also overlaid our a plot database that Alex here, the host, has kindly shared with us, and we're doing an analysis intersecting these plot locations with LiDAR-derived fuel metrics, or LiDAR-derived vegetation metrics that we're using to predict to fit fuel models. A couple of things I want to note here. So this map on the left is just the Forest Service website map, and you can see the North Kaibab district in green. That corresponds to the 2019 LiDAR collection here in our main map in the lime green outline. But prior to that, there was a collection in 2012 in the purple. And then last year, I actually found funding myself to fly post-fire LiDAR over these two fires, the Castle and the Ikes fires. So that's what gives us the post-fire measures we need to capture the post-fire conditions. And then we'll compare that to the 2019 data for the pre-fire conditions, which was fortunately flown just before these fires burned. We only got the data delivered though a few months ago, actually, not only 2020, but 2019. It was hung up in QA/QC a long time with USGS. The plot data date all the way back to, I think, 20 years ago or so. And so the 2012 LiDAR collection will also come in handy because we want to relate the field measurements on the ground as closely as possible to the LiDAR collection date to get better fitting models. It's important to make that temporal relationship as close as possible, but then also the spatial. We want accurately geolocated field plots so that we get a good spatial clip of the point clouds from which to calculate metrics to then compare to our fuel attributes measured in the plots. Now, I got interested in this area in 2016 on a site visit, and this area I'm going to outline now, the tip over area, which spans the boundary between Forest Service and National Park Service lands, is interesting. There's a lot of plots there. On the eastern half is more kind of mixed conifer, and the western half is more drier, lower elevation ponderosa pine. And you can see that, and so I found a report of the tip over fire from 2013. So there is some existing data based on a lot of these plots that we can also use the older measurements. And then here, just to kind of simplify the map you're looking at, showing those plots again, and then the Ikes fire perimeter and how the perimeter burned through, it looks like 7 of the plots. So there's actually an opportunity here to go do post-fire measurements that are co-located with earlier measurements on those same plots. And I would have liked to have done that last year, except COVID kept us from going and doing the field work. But maybe we can still do that. Similarly, we want to intersect all these other plots, which are kind of confined to the southern portion of our study area, intersected with the fire history, because time since fire has a big influence on fuels, particularly the surface fuel loads. In fact, just looking at the database already, you can see the variability in surface fuel attributes. So this is a stacked column graph across the 152 plots that we're looking at this time. And you can see that often sometimes more than half of the total surface fuel component is litter and duff, whereas the rest is the fine woody and the coarse woody, which is the 1,000-hour fuel. And so this is another representation of that variability in these box plots. And then from my 2016 site visit, I have a pretty good idea of the conditions that are out there because we went to both ponderosa pine and mixed conifer forest to see what it looked like. So some preliminary models, we found that we could actually explain 40% of variance in the total surface fuel load, which is encouraging. It's already better than we're doing at Williams Flats. And then when we partition into those two different surface fuel bed components, we can do better on the fine and coarse woody debris. And we do worse on the litter and duff. And that's as I would expect. I mean, the sensitivity of LiDAR, it's greatest for the canopy fuels. It's less for understory. It's even less for the coarse woody and fine woody debris on the ground. And it's the least of all for litter and especially duff. Just diminished sensitivity, the way LiDAR works. So here's a busy graph, but I just want to show you that we have published on this approach, this indirect approach using pre and post fire LiDAR measurements. So in this study, we use the opportunity of pre and post fire field plots and LiDAR collections at 2 fires. And these were the 2011 Los Conchas fire in New Mexico, and then the 2012 Pole Creek fire in Oregon. And the idea that we tested here for predicting tree biomass, which is shown on the top row at both fires, surface biomass below that. So that's like canopy fuels and surface fuels. And then we also predicted canopy bulk density, which is an important parameter as input into fire behavior models. And then we wanted to say, okay, if we just fit completely independent models, a pre-fire model from pre-fire fuel plot and LiDAR data, and then a separate post-fire model from post-fire plots and post-fire LiDAR data, and difference those, how does that compare to just using a pooled data approach where we put all the plots in a single model, both pre and post-fire plots, and use that model? And to just cut to the chase, this pooled approach works better. You double your plot count, assuming you have an equal number of pre and post-fire plots, but then you also just better represent the highly variable fuel conditions that are out there when you have pre and post-fire measurements. Because as I mentioned, post-fire conditions have varying degrees of change from the pre-fire condition. And so low, moderate, high severity, you could have minimal impacts on the canopy or the fuels, moderate, or complete consumption. So we took the pooled model approach as the best one and applied it to generating consumption maps at these 2 fires. And that's what represented here in these figures. So this is tree and surface biomass. The top row is Pole Creek, and the bottom row is Las Conchas. And we had broader, lighter coverage post-fire in the case of Pole Creek. So it's actually a little bit more interpretable because you can see that the outside areas contrast with what was inside the fire perimeter. We also used that opportunity of those 2 fires to look at satellite-derived FRP measures as a way to estimate consumption via the direct approach. And so that's what I'm showing here in this graph. So the top row, comparing the pre and post model to the global model, which is that pooled approach on the right. And if you select MODIS pixels that had at least one observation, you get pretty good linear fits between the rate of energy calculated from the MODIS pixels and then the total fuel consumption that we calculated by our LiDAR-based approach. And then if you whittle down those pixels to where you had more than 5 FRP observations for a given pixel, then we didn't actually see much difference. We got very similar estimates by that. So the approach that's sort of cooked into estimating FRE from MODIS satellite data, FRP observations, actually works quite well, regardless of the number of pixels in this case. So anyway, but it's good to see that linear relationship because that's what we expect in theory. And the final thing I want to present to you today is some work I did in Florida, where this is where we compared the LiDAR-based approach to estimating fuel loads to the FRE approach to estimating heat release and then getting consumption from that. So on the left is a fuel map of pre-fire fuel conditions at Eglin Air Force Base. And these are different replicated burn units that we burned in that study. It was called the ARCS Cadre study. And the darker green areas represent higher surface fuel loads. And some of these units are forested. The bigger units, 703C and 608A, and then the L2F unit are forested units, whereas the other units labeled here are all non-forested. So it's sort of a mix of small shrubs and herbaceous weeds and stuff. It's actually a bombing range. That kind of elongated study area on the left is a bombing range for the most part. And then the green dots represent our fuel plots on the ground. So that's an estimate of surface fuel loads derived from those fuel plots and LiDAR data collected just before the fire. And then we didn't, unfortunately, have post-fire LiDAR data for that experiment, but we did have active fire airborne thermal measurements from which we quantified FRP and then integrated over time to get FRE. And here you can see the FRE patterns across these landscapes. And it looks like you're seeing fire lines, but actually that's sort of an artifact of the sampling. The fixed wing aircraft flies over at about 3-minute intervals, and so it misses a lot of the fire progression. So we did a subsequent paper that I'm not going to talk about today, but you could look up where we krieged between the FRE estimates to get what we think is a more accurate depiction of the energy release, from which you could then also estimate consumption. So by these two approaches, I took the pre-fire fuel estimates from the LiDAR and predicted consumption based on our percent consumption estimates from the plots on the ground. And then from the FRE data, we converted that to a prediction of consumption represented on the x-axis. So this lower left figure here shows the summarized airborne WASP. It's called the WASP sensor from long wave infrared radiation. And we are converting the FRE to an estimate of mass loss. And that conversion, you have to also account for not just the radiative heat flux, but also convective heat flux, which is a larger proportion of the total heat flux. When you do that, and that's what this maximum and minimum radiated fraction represents. So when you have a lower estimate of what proportion of the heat flux is radiative heat flux, you end up with a higher estimate overall for total heat flux to then convert to mass loss by consumption. So that provides kind of a measure of variability here. So this is aggregated at the whole unit level, and except for the L2F units, these other units were a little bit under-predicted relative to the observed consumption, but the L2F was slightly overestimated. But then we also had these ground sensors, and the picture on the right shows what one of those types of ground sensors. It's a pocket radiometer, and it's up there about 20 feet above the ground, looking down, and the fire passes underneath it, and it measures the radiative heat at 1-second intervals, the FRP. Or from the voltage measurements, we can get FRP and then integrate to get FRE. And so this D plot here, you can see how those measurements fall really nicely on the 1-to-1 line. And that's because it's getting the whole fire progression at 1-second intervals. It's not missing a lot of the observations. And that's the hardest thing about the FRP approach. If you're doing it via satellite, the satellite only passes over twice daily. So it's hard to get a more accurate energy estimate. And then we had other types of radiometers too, from which we're estimating FRE on the ground. So this is encouraging. We want to see a linear relationship when you predict mass loss from FRE to actual mass losses observed on the ground. And if you're wondering what that kind of fire looks like, here's a picture of that burn for the L2F unit. So that was one of the forested units. These are understory surface fires. They're not much, small flame heights, no more than 2 meters. They tend to burn every couple of years to keep the shrubs down. And so it's a nice place to work to make on the ground measurements, because your instruments and equipment don't all get burned up like on Western wildfires they might. Okay, so to wrap up here, in conclusion, I want to impress on you some take-home messages, that fuel beds and the fuel components that comprise them vary tremendously in space and time. So that makes them difficult to measure and to model. We can improve our estimation of fuels when we use local field data and LiDAR. And sorry, my phone rang. And then we can reduce, by so doing, we haven't thoroughly tested this yet, but we're still asserting that we can reduce the uncertainties in estimated consumption, and then in turn, emissions estimated from that consumption. And so that the consumption, estimating consumption by sort of the three approaches that I've gone through today, it's challenging in every case, but each method has its advantages. And I'm not trying to show that any one of these is better than the other, because I think we actually need them all to make progress in the fire science. But an advantage of the indirect model-based approach is that you don't have to rely on local fuel measurements. For large scales and for quick answers, you want the model-based approach. However, when you do want more accurate local estimates, and you have the opportunity or availability of local data like LiDAR information, then it would be great to leverage that information. And then the direct approach to fuel consumption estimation is actually appealing because it is direct. We're actually observing consumption as it happens. And so I think that has the most promise for sort of like global, especially fire monitoring and estimating how much consumption is happening from satellites. But we need a satellite network that can provide us sufficiently frequent observations to get enough FRP measures to really get good energy flux estimates. And I will leave it at that. I have 46 minutes, so I hope I didn't go over a little bit.
Oh, that was amazing, Andrew. Thank you so much for the great presentation.
You're welcome. It's a pleasure. Thanks again for the invitation.
And with that, we'll move on to any questions. I don't see anything. Oh, there we go. Cool. We got a chat from Dr. Poulet.
Should I stop my share? I suppose so.
Oh yeah, please stop your share. And can you open up the chat? Got a question.
Okay. Yes, Pete Poulet asked, and I understand you presented a week ago, Pete. I wish I'd been there for that. I'm sure it was good. He asked, he's curious whether when I fly active fires, does the smoke itself and large materials in the column degrade the LiDAR accuracy? Oh, so yes, I'm sorry if I gave the impression that these LiDAR collections that I'm talking about happened at the same times as the emissions measurements. No, the pre-fire LiDAR data was sometimes collected 1, 2, or even several years in advance. I think the fires that we selected, it's no more than 4 or 5 years in advance. And then we contract the post-fire LiDAR, and if we're lucky, like at Williams Flats, we were lucky and we had the LiDAR flown about a month after the fire burned. But in the case of the Castle and the X fires, it was a year later. So yeah, there's no conflict between pre and post-fire LiDAR collections. Now, I will mention though that these airborne campaigns have airborne LiDARs, and they use LiDARs to look at the emissions themselves and the particulates. And I'm not an expert on that, but you can also talk about atmospheric LiDARs, and they provide amazing data for getting the three-dimensional shape of a smoke plume. So that's important data for plume development studies.
Cool. Awesome. Thank you, Andrew. And we have one more from Ryan Blackburn before we move on to the after seminar. Hi. Yeah, Andrew.
I can hear him.
Perfect. I'll just talk for a little while. So your comparison of the fire and the Los Conchas fire, looking at like the surface job, we did a job of predicting the Los Conchas fire, and just based on the R squared values, and I was curious why you think that. If surface biomass.
Okay, you were going in and out for me. I heard about 30% of that question. Sorry.
Hi, Andrew, can you hear?
Yeah, you're still cutting in and out. So was Alex actually in the introduction. I'm not sure why. I hope that wasn't the case for my talk, that you only heard 30% of my words.
Well, we heard you the whole time. Can you hear me better now?
Yeah, yeah.
Oh, okay. Essentially, I was asking in your Los Conchas, and I had it pulled up on my phone. Something pole fire. There's your surface biomass predictions were much better, and I was curious as why you think you're able to have better predictions of surface biomass.
Okay, you were still cutting out a little bit. You were asking why they were better surface biomass predictions at Pole Creek instead of Las Conchas?
Los Conchas instead of Pole Creek.
Okay, Las Conchas instead of Pole Creek. I think actually it was the plot data. This was an opportunistic study, and the plot data that was collected at Las Conchas, if I remember right, was just a better representation of the conditions out there. Whereas the Pole Creek plots, I think they were FIA plots, and they sample on kind of like a set schedule, 10% per year. And so there might have been fewer plots characterized at the right time, and probably more variability in time between the plot visits for those data.
Cool, thanks.
Yeah. Yeah, so the fire wasn't the primary purpose for those plot measurements. Okay, here's a question from Tom Kolb. Can satellite-based sensor approaches that measure atmospheric CO2 directly be used for assessing fire emissions? And how accurate? Yes, I think so. This is not my wheelhouse, but I've at least met some other people who work on these kind of data from these airborne emissions campaigns, and they also work with satellite data. So yeah, the CO2 flux measurements, I think they can do that. I'm not so sure about how that's done, but for the first NSF project I mentioned in this talk, it's called the VB Flux project. They measured CO2 and CO ratios from the aircraft, and they are trying to get mass flux estimates from that data. And they actually told me that they would have them in September, and it's September 1st, and they haven't showed it to me yet. I'm interested to compare their mass flux estimates from the emissions to what we are getting for some of those fires based on our, completely independent approach, assessing consumption on the ground. If they line up, that's going to be amazing. Yeah, so I can't answer how accurate they are. Sorry. probably not very accurate at a local scale.
Cool, awesome. Well, with that, I think we'll wrap. At least for me personally, this really illuminates the complex interaction between fire and forest ecology, and respectively, seriously for me, how we as managers rely on research itself to measure and dissect these relations. So thank you so much for your hard work on our behalf on the KIBAB, and we'll give you a break before 5 o'clock.
I'd just like to say that, you know, it's also really fun and engaging, I think, to as a researcher to work with managers such as yourself, because you have that perspective that we sometimes forget when we get down into the weeds of our data sets. And so I look forward to working with you more on this North Kaibab data set. I think that's going to be interesting.
Oh, it's going to be fantastic. Likewise. Okay, great. Well, thanks for your time once again, and we look forward to seeing you in a couple of minutes. But yeah, thank you again. Much appreciated.
Okay, I'll be there.